Thank you very much. And thanks for giving me the opportunity to talk about maybe more the user's point of view on all the analytics we learned today. In our lifetime testing, test and reliability we do here in Erlangen. Tobias this morning skipped this slide, so sorry for bringing it up again. As mentioned, we are the Power Electronic Institute within the Fraunhofer Society, and we do semiconductors, but we also do the systems. So we do materials, we grow our silicon carbide epi, we do wafering, we do processing of devices. So we have a front-end fab over there. We build our own devices, and we do first-level packaging, means chip on substrates. And test and reliability, that's where I am. So in between the chairs but we also build cars, motorbikes, airplanes, electric flying just for fun, or in student works and in academic research. And we also know how to do electronic systems on a larger scale, transmission lines and so on. So what I want to show you here is basically where I'm from, here from the test and reliability. And this is the subject we are normally dealing with in our developments. The buzzwords are the digital twin. Sorry, wrong button. The digital twin lifetime prediction. This is a hot topic at the moment in society or in community. We do analytics and characterization. So I learned a lot on this subject today. And we do, and that's the core of our business, is device and module testing. Normally, it's environmental testing like you do in your laboratories as well. And there are some specifics to the power electronic systems we are using here in our institutes. So let's jump into the device test first. So that's really the application side of all the test methods. So the most important test or the most important feature in power semiconductor is, okay, you want to have high currents and you want to switch them with a chip, but the biggest problem is get away the heat. So imagine you have a 100 kV converter in your car, electric car, and you have 1% loss. You have a 1 kV heater, a sauna oven on the fingertip of a chip size. So and that's the basic problem of power semiconductor. And all I'm talking about is get rid of the heat and compensate for thermo-mechanic stresses, strains, and whatever, which may destroy your device. So one important part is thermal characterization. I don't go into the details. This is like a power system would look like. Normally you have a substrate, you have a chip on top, and believe it or not, we still have wire bonds a lot as a standard topside contact. The backside of the chip is typically soldered. And all these connections can fail if you do a lot of temperature cycling. And the other test, which is very unique to power semiconductor, is active power cycling test. So we give a current to a chip, we heat it up by the heat dissipation of the chip itself, and it's cooling down. Like you have in the car when you press the pedal and release it, we have these thermal cycles, and we are pretty well equipped to do these testing. So that's the marketing slide on the AQG qualification test. So this is a test set of procedures you have to do. For example, for your electric car, not to fail, the automotive industry asks for a really long list of tests, which we have here in-house and offer as a service, and where all our analytics works is going into. We have those, we are talked about degradation under voltage and current flow, bipolar degradation in silicon carbide devices. This would be then the macroscopic test for this high temperature gate stress test, dynamic gate stress test. So this is related to the stuff we discussed in analysis, and we do it on the macroscopic side, really stress the devices. The next one, let's talk about characterization and analytics. So it's all about how is the structure mechanically. We characterize also electric features, and for sure we do failure analysis and physics of failure models. And this picture show our standard tear down technology, which is a sort of more a sculptural artwork. So we are not doing AFM on our system. So because the systems are bigger, and we really made on one hand tear it down like this. For example, if you look into a capacitor, a DC link capacitor is in every electric car as an energy storage. I don't go into detail. It's a macroscopic device. And when you look with advanced technologies on such a capacitor, like you do X-ray tomogram, basically the material contrast may be good on other devices is so low that you just see the metal, but not what's inside the device. So you see mechanical tear down in some occasions is much better than an X-ray. Not always true. From the lifetime and analytic side, what we are investigating, for example, is inside such a capacitor, you may know from your student days, those capacitors you have called wounds. So dielectric and metal as sheets together wounded up, and this is basically the film capacitor. So this is how it is done when you do the production. And what we are interested in our tear down, would be the failures in such a system, and how would the metallization films, 14 nanometers on top of a 2 micrometer PE foil, for example, how would they react to all the possible aging and failure mechanisms? So when you look at this, the scale is very, very big. So you have a hammer and a Meißel, sorry, I don't know the English word for that. Thanks. And you go down to nanometer to observe the fail of the metallization. So, okay, we are not have this sculptural artwork. We also use the focus ion beam to really go down into the details. And for the intermediate analysis, we use an ultra-short pulse laser. We discussed also in the previous talk to section the region of interest we are working on. Let me give you an example on how our lifetime testing would work. For example, we had a nice presentation of EKTS on ceramics. So sorry talking about ceramic capacitors, but on our side, from the application side, we don't only have foil capacitors, we also have ceramic capacitors in such a, this is what I would call a converter. So this is basically the gas pedal, the pedal of your electric car. And if you include if you bring the capacitors very, very close to the electric switches, you have some advantages like fast switching, lower losses, less parasitics. But the downside is this electronic is hot, maybe 150 degrees or hotter. A film capacitor will not survive it, so you need a different material, and people want to do it with ceramics. The interesting part is what happens if one of those hundreds of capacitors fail? Will the device explode, and how will this sort of be relevant for lifetime and reliability of such a system? So first, you have to understand the structure of such an MLC capacitor. Basically, you have an electrode on the one side, and on the other side, a plate capacitor, like in the foils as well, and they are stacked, but not wounded up, but stacked in a ceramic. There are some tricks, like make an internal series connection for some reason. But basically, you need to understand the internal structure. If you want to discuss about failures or the root causes of failures, we are using a broad bunch of analysis technologies. The scanning acoustic microscope, the X-ray, the EDX and EBSD. And when you look at all these pictures, they are not really convincing in terms of resolution and to really attribute failure modes. In the end of the day, it's the crosscut, the painful crosscut and preparation to find some of the root causes. And to my understanding, the problem is the scale here in the dimension that the X-ray does not resolve here this big crater, which you see visually, and this delamination you see here slightly is very fuzzy in the SEM. So we are using a real broadband of mix and try to use the PEST method to identify the failure. Let me skip that. These are typical failure pictures. When you age your capacitor and you apply a voltage, then you get funny defects, chain defects, craters, edge defects. You have delaminations inside. You can understand the root cause if you understand the structure. Here we have a electrodynamic simulation. You see the location where this crack is always where the biggest field gradient is in the device, and this is how we analyze. So it's always structural analysis. How does the system really work? And finite element simulation helps a lot in attributing the mechanisms. A typical experiment for us is have the capacitors tested, for example, up to 2,500 volts at different temperatures. See when they fail, look which failure mode is attributed with this. We do this with the different materials and try to find out a systematic behind, which not always we are not always successful in this, especially on the real products out in the market through capacitors and devices. Basic monitoring items, for example, is leakage current or capacitance. You see some devices have a very low 10 nanoamps leakage current and a very stable capacitance. The other materials have a different behavior in the leakage current over time, 1000 hours at 150 degrees, for example, with a 2000 volt bias. So the leakage current is increasing, or they're actually failing very fast here as with a thermal runaway. So these would be a standard picture of the data, and then you try to derive some models. Unfortunately, in this field, we have a lot of empirical models, like the Prokofiev-Vasquez model for the lifetime of a capacitor, which simply compares, okay, if you apply a more voltage, it might live shorter. So by an exponential law, there has to be something to do with temperature maybe. So let's use a Boltzmann and have an activation energy. So these are real empirical models. And if you want to parameterize them, you have to do the experiments to 1, 2, 3 parameters. So 3 runs with different parameters to get a model out of this. And if you do this, or we do this as the industry does, there are more advanced capacitors, more advanced models with more parameters. So to my understanding, no way to parameterize them as a standard routine for reliability methods. So I think we are at the edge where you really can use empirical models for lifetime prediction. Let's have a look at such a failure picture. So just for fun. So this here, the devil of the failure is sitting everywhere. And it's not only in the capacitors. And thanks to our colleagues, I forgot to mention of Fraunhofer IMWS in Halle, which supported this work to a great extent. But okay, we talked about obvious failures, cracks, delaminations and stuff. How's about hidden failures? So this is a typical problem a customer would have. He has a molded devices, somewhere is a chip inside, and he comes to us and says, this is not working, leakage current is too high. So when you look with a microscope on such a picture, okay, there is something strange, there is a residue, but is this the root cause of of the increased leakage current. So what we do is we use, for example, lock-in thermography to identify the location. So this is a microscope picture. In the lock-in thermography, you would send a current through the device, apply a voltage, and at the location where is the defect normally is the highest leakage current. So this device will heat up. And this you can see here in this picture, so that the location of the defect is not here inside, it's just at the edge of the device. And you also have in the lock-in thermography, so we can discuss about the method later, you also have a phase picture which gives you an indication on the depth in the substrate where it is. The funny thing is, in principle, you can look through polymers really inside. You don't need to have a flat surface. It's like it's a very useful method for our type of products to analyze where just by heated raise of temperature where a potential defect could be. And here are other examples. Now we drill down and you really see here the gate structures and that it's obviously a problem here at the corner at the guard ring, where's the root cause. And now you can use your FIB and make a picture. If you would have looked at this structure, no way where to dig. Okay, that's basically the equipment we are using. It looks like a microscope with an infrared camera and oscillating power supply. Okay, let's go on the digital twin lifetime prediction side, or the more material science side of my group. We do a lot of reverse simulation, what we discussed earlier. Most of the material parameters we are looking in, like internal stresses and elastic parameters, are not accessible by a direct measurement. So we do a simulation to derive them. And so that's why we do in this group a lot of simulation as well, not just analytics of material. In our group here also, we do a lot of macroscopic simulations like thermal, like fluid dynamics, parameter studies definitely. But what I want to more go into at the moment is the structural damage we observing from FEM side. This would be a typical approach on a lifetime analysis and lifetime prediction. You have on the one side, you have the experiment, for example, a power cycling experiment. You heat up the device with a certain T on time, 3 seconds. You let it cool down. You have a delta T, that means a temperature drop, something like 120 degrees, for example, for the chip. And you do this 1,000,000 times, 10,000 times, 100,000 times, or 1,000,000 times. And then sooner or later, a crack, for example, chip on a substrate, and the solder layer will generate a crack. And with the crack propagating, the device will fail because the temperature is getting higher and higher and higher. And with this, you can do an empirical lifetime model like most of the industry does. You calculate an accumulated damage, and you can say, okay, my lifetime is more or less eaten up to 80%, and I have 20% very likely lifetime of the device. And what we are doing is, or what also the industry is quite commonly doing, you have a mission, and you want to relate this academic test to the application. So you need a mission profile. That means like, how often do you press your gas pedal? How do you often change speeds? You have a mission profile over time. You translate this mission profile into a temperature profile. You count cycles. You try to, or you're calculating basically a load profile. So which should be similar, or should be somehow similar to your testing. And to achieve this, we use this load profile in simulation to calculate the effect on the structural integrity of those systems. For example, in this chart, we are calculating the heating and cooling cycle in an FEM simulation and look at, some of the pictures we lost here. We look at the temperature in the chip. Here you should see the bending of the chip itself and the bending of the wire bonds. And in the lower picture, you should see how the plastic strain in the wire bond and the plastic strain in the solder layer is changing with each cycle, and the accumulation of this plastic strain with each cycle, it's accumulated until the device fails, the solder layer fails, until the wire bond is failing. So this is the way where we really calculate lifetime on the cycling, and not forgetting that you cannot use literature data on when you do your simulation, because when you talk about a chip solder to a substrate, you had the chip and the substrate at 230 degrees when you were cooling it down. So the internal stress in the system is not equilibrium, it is pre-stressed. And that's also accelerating the failure. So you need to not only simulate the use case, you also need to consider in simulation the production process. Second part is, we also, as mentioned, we use simulation for reverse calculation or reverse simulation of internal parameters. And I give you an example on this. Sorry?
You have 3 minutes left.
Yep, thank you very much. And I give you 2 short examples on what we do, for example, with the simulation and investigation in the reliability. We use, to quite some extent, our focused ion beam. Thanks, Matthias, for your support all the time. And we do, for example, have a micro pull test inside. And that's a pain for Matthias, who owns the equipment, because in a vacuum chamber, we have cooling water and we have 500 degrees. Because we have to characterize the material in application relevant regimes. And this will be from room temperature to 300, 400 degrees. So, and this is what you can see here, sketch from the microbench. And now I want to show you, this is a sinter layer of, when you mount a chip to a substrate, underneath there's a chip to the substrate, you can use a solder or more reliable a sinter layer. The problem with the sinter layer is it's a porous system, and the size of the pore depend on the fabrication process, how much pressure you apply it, and so on. If you want to do a simulation, these pores are something like 300 nanometer size. The system is something like 10 centimeters. So when you want to do a simulation, no way, these are too much scales to cope with an FEM. So you need to get a material model for the sinter layer to be able to use it in the calculation. And this is what we do, for example, with the FIP and the SEM. We do a 3D tomogram of a representative sinter volume, about 3 micron, and the voxel size would be 9 by 9 by 20 nanometers. That's a bit of painful and lengthy experiment. Basically, for this data sets is a year's work. But what you get is, is not the sinter material, this is just the pores. So they're not connected, in this case with the different colors, not connected voids. And if you have another sinter layer, which is more dense, it would look like this or like this. And we put this information together in a sort of, we call it homogenized structural function, where you really can derive in the simulation something like stresses and elastic strains out of this data set, taken at different temperatures, taken at different temperature and processing parameters of the layers. And with this set of information, you can now say, okay, this is a Van Mises plot. These are the strains in the different space directions. You can say, okay, this is acting inside. You have elastic inside these three-dimensional space. You have elastic behavior, so everything is okay. But outside, you would have a plastic deformation, which may lead to a fail. And so these are the material models we are using for our simulation, and which we need to generate from analytic works on the FIB and SEM and so on. And this is really the second last slide on that. Another example would be reliability of thin films. I think all of you have seen this in their lives earlier, delamination of metal films on semiconductors. There is a pretty nice method which is discussed in literature about 10 years ago, the CSN method, where you put with a nano indenter from the side of the chip, you have a chip, silicon chip with a metal film on top, and then you push from the side with a nano indenter in. This will generate a crack, or this will generate a segment of silicon, which is then pushed up and will delaminate this film. So this is the method we are using to characterize with geometry. That's the literature, how the literature does it. With the sort of the opening of this delamination, you can attribute this as a relative comparison of adhesion. But our way is to do it again with a reverse simulation. And I don't go into the details here of this method in the scope of the time. So we do the experiment. We do a parameter study on the adhesion forces, or the surface energy basically is the target, and we benchmark and validate it against our experiments. And the important point is here that we really get a number for surface energies of a thin film on top of a silicon in terms of calculating adhesion, and use it in reliability models when you want to do reliability prediction. So as a summary, it's a bit different from AFM and SEM. We are just using them as a tool for macroscopic lifetime. The issue we have is the big scale difference you have to cover from nano to centimeters or meters even. And thanks for your attention. And if you have more questions, I would be happy to answer if I can. Thanks.
Thank you very much for the presentation. We may have time for one quick question before we go on to the next talk. If not, then we'll wait for the discussion panel to see if there are any other questions that come up. Okay, anyone on site have a question? Okay, Alex.
Thank you very much. Maybe just a brief question. Could you comment on the resolution of this log-in thermography? This looks quite interesting.
In terms of temperature or a spatial resolution, basically it's a microscope. So factor of 60, what you expect on a microscope. The problem on the resolution is, but it's not the optical, it's the sort of the blurring. So the temperature propagation. Temperature will not be localized. It will be spreaded over the whole device. And what you do, we have about a 50 hertz signal, heating, cooling, heating, cooling, and during this time, the thermal energy will propagate. So I think it's not limited by the microscope itself or by the video camera. It's limited by the material. And the deeper there is, it's blurred. So if you look, maybe what we also do, I showed you the device. We can, the beauty is you can look through molds and polymers. The only thing is you will get a more fuzzy picture. And then you remove the polymer and look again and go step by step down. So it's a very, you use it like a microscope. It's actually that simple for localizing, leakage currents or power dissipation. And that's the downside. You need to have a power dissipation. So you need a milliwatt or maybe a tenth of a milliwatt. So to generate a heat rise. The heat rise you can observe maybe in the millikelvin regime, even though you are at room temperature. You see it 2-3 millikelvin, but this is due to the lock-in technology. No? So if you want to have more resolution, you have to measure longer.